A language, a large language model-based framework for enhancing the integrated regression. As the complexity of the modern digital giants continue to grow, the verification process becomes increasingly resource-intensive. Among the phases of the verification process, integrated integration relation is particularly time-consuming and requires extensive manual effort. In this paper, we identified three major challenges in integrated regression: test cases, prioritization, optimization, log volume overload, and data availability. To address these challenges, we propose leveraging the large language model to advance the robustness and efficiency of the verification process. One introduction. As modern digital designs grow increasingly complex, integrated regression has become a critical phase in the verification process, ensuring the wide system-wide functionality. While integrated regression involves learning numerous test cases with limited resources, so the system-wide it presented challenges in managing the failure, analyzing the result, and prioritizing critical test cases. However, the priority of the test cases can change depending on the verification context, making it challenging for verification engineers to manually adjust the priorities. Furthermore, analyzing the result requires engineers to manually correct the error messages from the logs and classify them, which is time-consuming, especially as the volume of the logs increases with the system complexity. These challenges can be categorized into three major obstacles: test case prioritization, optimization, and log volume overload and data availabilities. The priority of the test cases is not static and changes throughout the verification process. In the earlier stages, test cases with a significant RTL changes will take precedence, as the design update often introduce critical bugs that need immediate attention, while in the later stages, unresolved failure become more critical to ensure the reliability. Traditional methodologies rely on a heuristic, which can be time-consuming and suboptimal for managing these dynamic priorities. A significant challenge in integrated the regulation is dealing with the massive volume of the simulation logs. These logs are indispensable for error analysis, but the volume of the data can overwhelm engineers, making it difficult to analyze and extract meaningful insights. Additionally, the duplicated errors across the log further complicate the process identify of the resolving the issues efficiently. The complexity of the data and documentations in the verification process, along with the complicated environment, present another challenges. The results and information are often scattered across multiple systems and platforms, making it difficult for engineers to extract and consolidate relevant data efficiently. To address these challenges, we propose a large language model LLM-based framework to streamline and optimize the verification process with dynamic weight adjustment for test cases, prioritization, log summarization, and clustering to manage log volume overhead. And the retriever augmented generation RAG enhanced agent to improve the data availability. Section 2 is related works. Recent studies have explored innovative approaches to improve the verification efficiency. For instance, reference 1 introduced machine learning ML-based techniques that optimizes the simulation regression by identifying the correlation between the randomization points and coverage from the previous regressions, along with a ranking approach that selects the high coverage seed. And so the reference 2 reviews the test case prioritization approaches in the regression, providing valuable insight into variable techniques and their effectiveness in software domain. In parallel, LLMs have introduced state-of-the-art technology and leverages across a wide range of the industry. The reference 3 proposes a tool augmented LLM methodology to enhance the accuracy and maintain up-to-date knowledge. RAG addresses challenge of LLM, such as hallucination and outdated information by integrating data from the external resources, thereby enriching the knowledge of LLMs. The reference 4 provides in-depth examination of the progression resources. Therefore, the in-depth examination of the progression of RAG paradigms, offering a comprehensive understanding of the advancement in RAG. Additionally, the reference 5 is excited for its contribution to the efficient memory management in LLM, serving through the introduction of page attention, which optimizes memory usage of enhancing model performance. The building of these advancements, we have a compelling opportunity to explore the application of the LLM and RAG within the context of verification regression. By leveraging capabilities of the LLM to process complex data and integrated real-time information, we aim to propose a robust framework that enhances verification regression efficiency. This integration represents a novel approach in the ongoing effort to tackle the challenges of the verification throughput. Section 3 is a proposed method. To streamline and optimize the verification workflow for engineers, we propose another framework utilizing the LLM to enhance the verification process in the three aspects. First, it dynamically prioritizes the test cases based on the verification stage. Second, it addresses the challenges of managing the overwhelm loads through the summarization and clustering. Finally, it integrated the RAG-enhanced agent to improve data availability. The Figure 1 is the architecture overview. The proposed framework consists of several components as illustrated in Figure 1, determining the execution priority of the tens of thousands of test cases in real time is challenging due to the limited data and the complexity of the manual assessment. We optimize the test cases prioritization by leveraging LLM alongside regression-related factors. LLM assigns set weights of these factors that may vary in importance depending on the contextual information provided in the prompt. Based on these weights, the framework reorders the test cases to ensure that the critical test cases are executed first, aligned with the verification context. A detailed explanation is described in section 3-A. The log summarization process addresses the challenge of efficiently managing large volumes of logs by using error messages from the log as input. So LLM generates summarized log data, which are then embedded and stored in a vector database along with the relevant metadata. This allows the framework to cluster similar errors for more efficient analysis and group test cases that encounter the same errors. By automating the summarization and categorization of the logs, the proposed framework significantly reduces the manual effort required for an error analysis. A detailed explanation is provided in section 3-B. Analyzing the regression result often leads to delays in the verification turnaround time. The proposed framework enhances the data's availability, improving access to a variety of the design and verification data resources. To achieve this, the framework utilizes a RAG-enhanced agent composed of the tool bound to LLM to handle the request of the verification engineers. This enables engineers to consolidate fragmented data and streamline the manual processes, ultimately improving the overall efficiency of the verification process. A detailed explanation is described in section 3-C. Test case prioritization optimization. The prioritization of the test cases is not static. It evolves as the RTL design matures, In the early stage of the verification, the frequent changes to RTL frequent changes to RTL design often introduce critical design bugs. Consequently, rapidly identifying and addressing these bugs become the essential. As RTL design reaches a certain level of the maturity, it becomes crucial to identify verification errors that arise during the execution of the test cases. In the later stage of the verification, test cases that consequently fail require prioritization attention. However, manually determining the priority of the tens of the thousands of the test cases in the evolving situations is extremely challenging for verification engineers. Furthermore, due to input token limitations, providing the LLM with the information of the tens of thousands of test cases simultaneously is impractical. To address these challenges, we propose a method to dynamically determine the priority of the test cases by leveraging the LLM-based on-score metric. We identified three primary factors that influence the test case's priority in a regression: change impact, execution cost, and regression history. The significance of these vectors varies depending on the context of the design and verification situation. The change impact (CI) reflects the extent of the modification made to RTL and each associated verification issues, each calculated as a product of RTL changes and updated issues count. Test cases associated with a higher CI values are prioritized, and they are more likely to be impacted by the design changes. Change impact is delta RTL multiply updated issues count. Execution cost issue. Estimate the time required to run a given test case based on historical data. This factor helps the balance of the trade-off between the importance and execution time of the test case. The test cases with a shorter expected runtime might be prioritized when longer test cases are scheduled when sufficient resources are available. Execution cost 1 over T expected runtime based on historical data. Regression history, RH, is considered the number of failed runs and time remaining in the failed state. Additionally, it applies a discount rate based on the latest status of the test cases. This factor highlights the test cases with a higher likelihood of failure and have historically been problematic, and making them prime candidate for earlier execution. The regression history is when n fail over n total by multiple times t failed times latest status discount rate equal 0.5 if passed, 1 if failed. So figure 2 is test case prioritization optimization. The figure 2 illustrate the LLM is utilized to determine the importance of these factors, which are presented as the weights of the score metric. The system prompt consists of the definition of the factors and contextual information from email, release notes, or issue report is provided as a human prompt to LLM, whereby LLM adjusts the relative importance of factors based on a given contextual information to adaptively optimize the execution order of the test cases based on up-to-date information. The output of the LLM is formatted in a structured manner to facilitate the computation, and the weights are applied to compute the final prioritization score as. Score equal WCI by change impact plus WEC by execution cost plus up WRH by multiply regression history. This score is used to reorder the test cases, enabling optimized test case prioritization tailored to the context of the design and verification situation. Second B is log summarization. The current process of log analysis presents several challenges. The logs are often large in size, making it difficult for verification engineers to identify the relevant information efficiently. Additionally, identical errors are frequently repeated across the multiple test cases, further complicating the task of pinpointing the root cause. And these redundancies not only increase the volume of data that need to be analyzed, but also reduce the overall effectiveness of error detection. To address these challenges, we propose leveraging LLM for log summarizations and storing the summarized data in a vector database, as illustrated in Figure 3. So, two summarization process can be the approaches using two main methods, wrap, reduce, and redefined approaches. The wrap reduce approach involves breaking down errors into smaller chunks and processing each chunk in a parallel to generate individual summarizes map. On these summaries are created, if the size of the total token exceeds a maximum token limit, the summarizes are repeatedly collapsed until the final summary is generated, reduced. This final summary integrated the numerous and unmanageable errors into concise and well-organized format. This method is highly efficient for handling large volume of data, so as it enables distributed processing for scalability and efficiency, significantly reducing the time required for processing. However, the drawback of this approach is that summarize processing, the summarizes generated for individual chunks may lack consistency or miss contextual information. This is Figure 3, log summarization, map reduce summarization. So, on the other hand, the refined approach processes the entire data as a single unit. It iteratively summarizes the data by the processing the first chunk and combining the summarized content with the subsequent chunks to refine the summary. This approach ensures that the context across the entire data is considered, resulting in more precise and coherent summaries. However, it can be slower when dealing with the enormous logs, as the entire data must be processed sequentially, which limits scalability. Among these two approaches for summarization, we opt for the map-reduce approach. While map-reduce has a potential drawback of the lower consistency compared to redefined approach, this issue can be mitigated by adjusting the chunk and overlapping size. This adjustment not only maintains consistency but also allows us to take advantage of the performance benefits of the map reduce. These advantages make it possible to deliver critical error information to verification engineers in a timely manner, ensuring that they can respond promptly and effectively to failures during the verification process. C. Data availability and with retriever augmented generation RAG enhanced agent. As verification processes proceed, the system accumulates various types of data, documentation, and issues. These data serve as critical metadata to verification engineers, enhancing both the accuracy and efficiency of the verification process. The engineers utilize this data to carry out the repetitive and standardized manual tasks, such as issue bring-ups, and bug tracking, and test environment setup, and rerunning the failed test cases. However, as design complexity increases, the exponential growth in volume and variety of data presents the significant challenges in accessing and retrieving and effectively utilizing. This inefficiency not only complicated the verification process but also directly contributed to the longer verification turnaround times. As verification engineers spend more time on the retriever and manual tasks rather than the focusing on debugging and analyze the result. The figure 4 is a RAG enhanced agent. The figure 4 illustrates the proposed method leveraging on RAG enhanced agent to address this challenge. RAG overcomes the limitation of the LLM, such as hallucination, outdated information, and untraceable reasoning, by integrating the domain-specific data sources that provide up-to-date relevant information. To further optimize RAG, agent is integrated into the framework, which is bound to several tools that streamline the verification flow. The agent intelligently reasons and selects the appropriate tools, including retrievals, searching from the design verification specification and documentations, and executors that perform tasks according to the prompts, and validators to verify the accuracy of results. These tools are designed to seamlessly integrate into agent, ensuring support for a diverse workflow, including retrieving regression results, troubleshooting, and navigating database. This flexibility, combined with the rich reasoning capability, make the agent as a powerful component for automating repetitive tasks and streamlining the verification process. Section 4 Result. The framework we propose is designed with the focus on delivering prompt responses to the verification engineers to enhance their verification processes while ensuring the high efficiency and high quality results. To achieve this, we opt for a Mistral 7 billion model without fine-tuning due to its robust processing capabilities and utilize the VLLM for serving and inference. This approach significantly enhanced performance and reduced memory usage, making the framework well suited for a real-time application. A. Test case prioritization optimization. To analyze the contextual information related to the design and verification, relevant documents and materials were reviewed. These documents and materials provided updates and details about the ongoing issues. For instance, the test cases with specific features that are experiencing issues or requested to add new features to certain blocks were included. Additionally, some materials emphasize the situations where the constraint on disk space and licenses requires prioritization of certain test cases. Design engineers also provided detail on which blocks had been updated and which new features had been added to the test cases. We analyzed two scenarios. In the first scenario, we assume that during the early stage of the verification, uh, prioritizing the test cases related to the changes first would help design and verification engineers identify design bugs more efficiently. The framework provided contextual information from the documents and material through the human prompt to LLM. Figure 5 is the LLM response of the test case prioritization optimization. The LLM assigned weights of the three factors as follows: WCI 0.7, WEC 0.2, WRH 0.1, as shown in Figure 5. The values for CI, CEC, and RH for each test case were calculated using the equation 1, 2, 3. 1, 2, 3. From 1 to 3, described in section 3-A, and the -8 and the normalized to derive the final score. As intended, test cases related to blocks with more extensive challenges were prioritized and received higher scores. This simulation result indicated that the total time required to complete test cases related to the RTL changes was 96.7 hours, representing a 79.1% reduction in time compared to the scenario where no prioritization was considered. As a result, test cases related to RTL changes were executed earlier, allowing design errors to be identified at an earlier stage. The optimization of the test case prioritization enables design and verification engineers to detect errors caused by changes more promptly, thereby facilitating the faster debugging. This method significantly contributes to enhancing the overall verification efficiency in this scenario. In the second scenario, in the late stage of the verification, the verification engineer's goal was to achieve the 100% pass rate as promptly as possible by executing the remaining failed test cases. The relevant context data of the verification were provided as a human prompt to LLM, and in this case, the weights derived from LLM for each factor were set to WC 0.1, WEC 0.3, WHR equals to 0.6. Since most of the test cases had already passed, they were assigned to lower priority based on the discount rate applied to the RH equation in section 3-A. Additionally, due to the minimal RTL changes, the CI factor had little impact on the final score. In this scenario, the test cases with higher RH and EC values, considering regression history and with shorter run times, were prioritized. The simulation showed that by applying the prioritization, the execution of the remaining failed test cases was completed approximately 12.3 hours faster than when no prioritization was applied. In this case, LLMs had to wait to the prioritized test cases with a shorter execution times in order to improve the failure coverage more effectively by identifying the failure sooner. Consequently, the test cases with longer run times were executed later. As a result, the overall execution times did not increase significantly. The verification process is inherently by dynamic and subject to the challenge across the verification various contexts. While we focused on the two extreme cases, so early stage verification was substantially RTL changes and late stage verification with a high pass rate. The results demonstrated that a prioritization of the test cases helped to identify errors earlier and increase the failure coverage, aligning with the verification engineers' intended goals. The effectiveness of the prioritization was particularly evident in these extreme cases, highlighting a clear benefit in terms of time saving and improved verification efficiency. B. Log summarization. To analyze the result and identify errors, the manual and time-consuming process of reviewing log, which exceed 100 of MBs in size, megabytes in size, requires a significant human effort. Furthermore, handling the large number of test cases, often reaching tens of thousands, added the complexity. These lead to delayed issue resolution due to the complexity and volume of logs. To streamline this process, an automated post-processing step was implemented after regression completion to summarize logs and store the summarizes in a vector database. We identified that the errors occurring within logs we used had relatively low correlations with each other, which led us to apply the map-reduce approach for summarization. The summarization process, which involved parsing error messages and performing LLM inference, was executed without prior pre-processing. This decision was based on the observation that pre-processing, such as removing numbers of special characters, often result in data distortion. In some cases, it even led to summarizes that were less comprehensible to the verification engineers. Notably, the file paths and a specific error context were retained in the summarizes, as these details were crucial for engineers to access the relevant files or resolve issues effectively. To further optimize the process, a cap of the 15 iterations was applied to the collapsed loop. If a summary was not completed within these iterations, the process was halted to prevent excessive computation time, maintaining a balance between completeness and efficiency. Figure 6 summarizes result. The reduce prompt used in the map reduce process, where a format was specified, LLM returned the result in the predefined format as illustrated in Figure 6. The average time and resources required for each step of this method were as follows. The log size averaged 184.404 megabytes. The error size was approximately 0.29 kilobytes, and the document size for each summary was 232 bytes. The time required for summarization using LLM inference through the VLLM was 5.15 seconds, and the storing summarized with metadata in a vector database took 0.009 seconds. So the size of the data used for analysis decreased by approximately 99.87% from the 180 84.04 megabytes to 232 bytes. Moreover, the time to search test cases by errors or metadata in the vector database, which contains a lot of 109 documents, was about 0.015 seconds. The retrieval time might vary depending on the number of documents in the vector database. But even so, it still presented a significant reducing compared to the manual process previously used by the verification engineers. This process demonstrated a high efficiency in terms of time and resource utilization, making it well suited for handling large volumes of log data. When searching for errors in the vector database, human prompts were compared to a store's error summarized based on similarity. It was therefore crucial to carefully formulate the prompt. This method was particularly effective when searching with contextual description the context of the errors rather than rely on the individual keywords or the error terms, as it often yielded more relevant results. Section C is data availability with the retriever augmented generation RAG enhanced agent. To increase data availability and reduce the overall verification turnaround time, while allowing the verification engineers to focus on their core tasks, the framework leverages RAG enhanced agent. Compared the workflow and time of the conventional versus the proposed method for the two common scenarios in the verification process. First, for searching the information about the clock in the design specification document, verification engineers follow the conventional workflow, which requires opening all related specification documents, manually searching for the keyword clock. The process involves shifting through the search result. Shifting or there another word has a different meaning. Anyway, reviewing the multiple entries to find the relevant information until the desired content was located. In contrast, by using RAG enhanced agent, the verification engineer simply provided a detailed prompt to that agent, such as asking for information about the clock in the specification. The agent legends utilize the spec retriever tools to retrieve the top 5 most relevant documents from the design specification, offering answer to the user request. This process, which took an average of just 0.03 seconds, also included clear explanation from the LLM and the related documents from the vector database, thereby improving the confidence of the response. The scenario of identifying and running test cases that are failed due to certain errors is a common situation in the verification process. In the conventional workflow, the verification engineers manually filter the logs from the previously executed test cases to identify error keywords and rerun the corresponding failure test cases. This process was not only time-consuming, but also prone to inconsistencies and oversight, affecting overall efficiency. With the proposed framework, the agent was asked whether rerunning test cases that failed due to specific error keyword. The agent legends to utilize query executor to generate a database query that was then validated by query validator to ensure the accuracy and correctness. Once the query was verified, it retrieved the relevant test cases and sent the result of the API executors that was designed to run the test cases. Critical aspect of this method was accurate and precise description of the tools, Proper documentation of the tools was essential to the successful execution of the agent, ensuring that the appropriate tools were selected. So the furthermore, careful consideration must be given to the formulation of the human prompt with the agent prompt. As constructing clear and explicit human prompt was vital for agent reasoning and tools invocation, minimizing the possibility of the invalid reasoning. Chapter 5 is conclusion. By leveraging the LLM, the framework optimizes test case prioritization with dynamic weight adjustments that adapt to the challenges in verification context, reducing reliance on suboptimal heuristics. Moreover, the framework uses LLM for log summarization and clustering to manage the overwhelming volume of the logs, making error analysis more streamlined and reduce the manual effort. Additionally, a RAG-enhanced agent is utilized to improve the data availability, ensuring the engineers access to relevant insight from diverse data sources efficiently. A. The test cases prioritization optimization. For the test case prioritization optimization, we conducted a simulation of regression results, considering three key factors that influence prioritization. The simulations showed that assigning test cases reordering based on the contextual information leads to more effective prioritization. It's important to note that additional factors beyond the three considered may influence test cases prioritization. To accommodate this framework is designed to be extensible, allowing it to incorporate new factors and adapt to challenges in volume values and meaning of existing ones. Currently, the framework focuses on the factors at the test case level. In the future, it could be extended to incorporate factors that are block or IP level, enabling the hierarchical approach to test case prioritization. In the proposed method, LLM determined the weights while factors affecting the prioritization were pre-calculated. As a result, there was no mechanism to reflect verification engineers' preferences of the test case prioritization. To address this limitation, adjusting the priority of a certain test cases through a variable that is added to the final score calculation or metadata-driven approach could be used to allow the verification engineers to specify additional prioritization factor. These approaches would provide greater flexibility and enable verification engineers to influence the prioritization process for specific test cases, offering a more customizable and adaptable solution for test case prioritization in the integrated regression. B. Log summarization. This paper presented an efficiency approach for log summarization through an automated process that integrated phase vector database, FAISS vector database, by employing an map-reduce approach with parallel and asynchronous processing. The time for summarization can be significantly reduced. Additionally, the use of the verification-specific fine-tuning model rather than a general pre-trained one is expected to produce more specialized and accurate summarizes tailored to the needs of the verification engineers. While we utilize the phase vector database, it does not natively support metadata-based filtering. As a result, data retrieval based on data metadata required manually filtering results after retrieving more data than necessary. This process often led to performance degradation as the volume of retrieval data increased. The result could not be considered metadata filtered. To address this issue, potential solutions including embedding metadata as a string within the page context of document or storing metadata in a separate database. These enhancements would enable more efficient searches and filtering, improving the quality and efficiency of log summarization and analysis in the verification process. C is data availability with a RAG-based enhanced agent. To enhance the data availability and streamline the repetitive manual tasks in the verification process, we leveraged the RAG enhanced agent. In this paper, a single agent was employed to handle all tasks, which revealed a decrease in performance and reliabilities of responses. For the future work, by dividing responsibilities across multiple agents, the framework would allow each task agent to focus on its strengths and expertise, enabling more efficient collaboration and handling of complex tasks efficiently. Overall, the proposed LLM-based framework demonstrates the potential of the LLM to reduce turnaround time and provide a flexible and efficient solution for the verification process, especially integrated regression. By addressing the challenges such as test case prioritizations, optimization, log summarization, and data availabilities, and streamlined the integrated regression, enabling verification engineers to focus on their core responsibilities and ultimately enhancing the overall efficiency and of the verification process. Okay, reference. So there are references. Okay, today I read this paper from the DVCON2025, a large language model LLM-based framework for enhancing integrated regulation. Thank you for your time. See you next time.